In this exercise, we want to practice once again a case of infinity times 0. Consider the limit e to x times arc cotangent of x for x approaching infinity. Let me sketch the two graphs. E to x looks like that. So for large arguments, this is large, so this goes to infinity. And arc cotangent looks like that. So for large arguments, it goes to 0. And we have infinity times 0, which depends on who is faster. Whether this goes faster to infinity than this to 0 or vice versa. So once again, the product AB can be written as A divided by 1 over B or B divided by 1 over A. And as before, one of these two choices helps, the other does not. So let's write it as limit for x approaching infinity. And if we write arc cotangent of x in the numerator and dividing by e to x, dividing by 1 over e to x means dividing by e to minus x. And now, if x goes to infinity, this goes to 0, this goes to 0, and we can try L'Hopital's rule. When differentiating arc cotangent, we get minus fraction 1 over 1 plus x squared, and when differentiating e to minus x, we have minus e to minus x. And we can simplify this to get limit for x approaching infinity. Minus cancel, and dividing by e to minus x is multiplying by e to x, so we end up with a fraction e to x divided by 1 plus x squared. And we have seen already that exponential is faster than any polynomial, so we have infinity divided by infinity, and exponential wins, so it will be infinity. Well, okay, let me compute this step by step. So this goes to infinity, so we can use L'Hopital's rule once again. And we have limit for x approaching infinity. Derivative of e to x is e to x, and the derivative of 1 plus x squared is 0 plus 2x. This is still infinity divided by infinity. So we can once again try L'Hopital's rule, and we have limit for x approaching infinity, e to x divided by the derivative of 2x is 2. Well, and now the denominator is constant, 2, and e to x goes to infinity, so we have infinity divided by 2, which is infinity. The alternative approach, when writing this product as a ratio in the different form, does not help. Let me illustrate this. So from here, we can continue here. So this is not wrong, but it is not useful. Let me write it. Limit for x approaching infinity, and we leave e to x in the numerator, and instead of multiplying by this expression, we divide by 1 over arc cotangent over x. And then once again, if x goes to infinity, our cotangent goes to 0 from the right. So this goes to infinity, and this goes to infinity as well, so we can try L'Hopital's rule to get limit for x approaching infinity. Now, differentiating the numerator will be very easy. Derivative of e2x is e2x, right? And now differentiating the denominator, this is something to -1, which is minus something to -2, arc cotangent square of x, divided by the derivative of the inner function, which is arc cotangent, and its derivative is minus 1 over sine squared. Sorry, divided by minus 1 over 1 plus x squared. No, because arc tangent is defined everywhere. Well, and let us simplify this fraction. So minus divided minus is plus, and we have a limit for x approaching 0. And now we have e to x times, and here we have 1 plus x squared times arc cotangent square, both in the numerator of the numerator, in the denominator of the denominator, which is equivalent to being in the numerator. So we have 1 plus x squared times arc cotangent square of x. Well, you see, it's even more complicated than the previous expression. e to x is here, arc cotangent, not squared that, and still multiplied by 1 plus x squared. So it is correct, but this is more complicated than the previous approach. So I don't suggest this one, I take this one. And we know already that the result was infinity.